Hello. Hey everyone, you hear me okay at the back? Standing room only. I will take that. Thank you very much for sticking around. That's awesome. Right, let's get straight into it because we have a fair amount of content. Kuber-what? Learning Kubernetes. What is it? What does it do? Etc. 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 I'm not going to go straight into Kubernetes because Kubernetes, without understanding why or how or what problems it solves, will be a bit pointless. So I want to start with a bit of context. I want to start with a bit of a history lesson, because all of this is about how we deploy applications in production. So let's go back quite a while, back to when servers were really, really expensive, and a company may have one, or if they're lucky, two of them. And we gave this server a name, and we knew this server, and the operations guy was militantly careful on who did and didn't have access to their server, and they knew where it was and what it looked like, and everything was great. And because we had this server, the whole point is to run business applications, to do something for the business, whether it's an internal application, whether it's something interfacing externally with our customers, like a website. We just need to run applications. So the business comes along and it goes, hey, we need this new in CRM or inventory management or this customer website. Can you install it on our server? And this application will come in some form of installer, be it, Linux, Debian, or apt package, or a Windows MSI, or an exe, or maybe just a tar file of files. Extract these binaries here, this library here, put this startup script here. However the application comes packaged, we will end up just putting files across our disk. And if you're a Windows user, user bin, etc. Instead, C Windows System 32 for libraries and program files, and you get it. So we install our first application, and everyone's happy. And then, because we only have one or two servers, and these compute resources are expensive, there's another application we need to install for HR or whatever. We install application 2. Everyone's happy. And then we come along and install application 3. And application 3 needs the same library that application 2 depends on, but a completely different version. So installing application 3 breaks application 2, which is no good. So to solve this, we go, we need a bit of separation of concerns. Along come virtual machines. And virtual machines allow us now to basically take that one expensive server and split it into multiple virtual servers. So suddenly, application 1 and application 2 and 3, they have their own installation, be it Windows Server, be it Linux. There is no way that those files are going to mess with the libraries of the other applications. So we've solved the problem that was causing us downtime with the previous way we were doing deployments. But we have created a new problem, because instead of managing one server, instead of always being consoled in, the operations guy to that one server, he is now managing as many servers as he has applications. He is jumping on and off servers, remembering which one he's on, which one did what. He also suddenly has a load more servers to patch and maintain, and are there security updates for this installation? Schedule maintenance for it. Do I need to rotate the log file so the hard disk don't fill up? Everything that was done once. We're now in a scenario where we have a lot more servers to manage. And when we have a lot of things to do in a given day that all kind of look similar to each other, and we're jumping backwards and forwards between servers, the applications aren't causing us downtime, but what started to happen was user error was causing us downtime. Someone had applied the wrong patch to the wrong server, or take the wrong thing down, or install the wrong things in the wrong place. So that gave rise to configuration management. We went, how do we solve that user error? How do we stop that being our problem for instability and downtime? And so user management arrived, configuration management, so Puppet, Chef, Ansible, pick your favorite. And the idea was, the operations guys now don't touch the servers. We write what we want the configuration to be in configuration management, okay? And we don't go and manually run those commands, which we might accidentally typo and we might make a mistake. We put the configuration we want into configuration management, and we let configuration management then go and apply that to the servers. And because we're running in VMs, we can actually spin up VM4, a completely non-production VM, and we can test our configuration management against that server before we let configuration management loose to apply those changes to our production server. So we make our, update this application or add this, configuration. We put that into configuration management. We test that on a brand new VM, and then If that VM was successfully updated and the application's still running and things haven't set on fire, we can go and apply that to production. And that works really well. Configuration management works really well until it doesn't. And when it doesn't is at about 3 a.m. in the morning when Bob, this operations guy, he's on call. He gets a phone call at 3 a.m. It wakes him up. And it's his boss's boss's boss saying that this application is down and they're losing $1 billion a minute and it absolutely has to be fixed right now. And what Bob says to this manager is, okay, well, what I'll do, I'll go into configuration management and make some changes to get some debug logs. And then I'll spin up another little VM so we can test that configuration management. That'll take about 20 minutes. And then once we've tested it on that, we can go and actually apply that configuration to the server and start debugging. Of course he's not going to do that. He's going to go, yep, sorry, right, jump on the physical server, and he's going to save the day. He's going to physically just go in an emergency and make those changes and work out what's wrong. And then Bob's going to come into the office the next day, and he's going to get on with his day job. He's a little bit sleep deprived. There's a lot of things he has on his to-do list. And those changes never make it back into configuration management. Whatever he did that evening, that 3 a.m. emergency, never makes it back into configuration management. And so configuration management can become like that Visio diagram of your network that you have on the wall. It'd be beautiful if that was how your network looks. But realistically, it isn't. That diagram was out of date the moment you printed it. Someone will have plugged something in somewhere that won't be documented. And configuration management becomes like that the longer it's used. And so suddenly, the next time we have a deployment, the deployment fails because configuration management doesn't actually know the real state of what's going on that system. So it can't possibly enforce. It works on the test VM because there's nothing that's been manually changed on the test VM. The test VM is a brand new install, but it doesn't work on this production VM that has history of all these non-documented changes. So a few quite clever, kind of forward-leading companies thought, well, hang on a minute, what are we doing here? Why on earth are we running configuration management against this test VM, this new VM we've spun up, seeing that works absolutely perfectly, and then going back and reapplying configuration management to production that may or may not, depending on how many years old that VM is, have all these undocumented changes? Why don't we just not apply it to the test VM, snapshot that VM image, that virtual hard disk, and then replace the old production VM with this one that we know works? So we ended up with these baked images, this concept of configuration management is still good, but instead of letting VM1 over months and years end up with potentially more and more undocumented changes, we limit the ability for changes to affect us to every release, because every time we make a configuration change, we're actually shooting the old VM in the head, and the new test VM, the fresh install, becomes our production VM. Does that make sense to everyone? It's just about all these steps we've gone through in a history to kind of realize where we were messing up in terms of stability and production performance and availability, and kind of all these tools have been layered on top of each other to kind of try and prevent that. And so if we actually look at this diagram for VMs, we spin up a VM, we have something install, whatever operating system it is on that, we then run configuration management against that and we're happy with it, we know it works. We take a snapshot of that VM, a VMDK, a virtual disk image in OpenStack, a VMware, a VirtualBox, or whatever you use, and then we can move that virtual machine image to wherever our production data center is, we copy that virtual disk, and we replace the production VM with this known good image. Now let's have a look at containers. And you'll see, when we build a container, that looks very, very similar to what I've just been saying about VMs. Effectively, containers give us this same ability to bake images. So we know that this is a given quantity. We know that if we then put it over there and run it, it will do exactly what we expect it to do. And again, containers are immutable. We expect to kill them and replace them rather than log into them and update them and fix them. And effectively, why containers have caught on is because it is, that VM strategy was a good strategy. It worked. It was a really stable way of making sure production stayed up, because you were limiting the amount of changes that could creep in. And containers basically do exactly the same thing, but the user experience around how long that takes and how easy it is for a team to get started with that process has gone from days or months to seconds. I don't know if any of you ever had automated like that VM lifecycle process where you'd have some scripts that talked to vCenter and spun up a new test VM and then did some kind of TFTP network booting with some automation to install like Linux and then report the IP into like another system so configuration management could pick it up and go and install the actual things you wanted on it and then run your tests and then, you know, go and tell VMware to snapshot it and, you know, all that. You know, most companies didn't get to that point. The infrastructure required to build out that system was just frankly sometimes more work than just the occasional outage because of people messing with VMs. Whereas Docker basically turns that entire process I've just described into, I write a text file with a few lines explaining exactly what I want in there, my application code, my dependencies, blah, blah, blah. I run Docker build, and I end up with that image. It's literally that easy. You know, a developer can do it. So what are containers then? We're effectively just saying they're a good way of packaging up our applications and dependencies. They are taking the best of that VM world and making it a hell of a lot easier to do. They guarantee execution consistency because we know it's that baked image. It's not going to change. We're just going to replace it. And it's a good way to keep your applications isolated without the overhead of VMs. Another benefit from containers is you're not lugging a 30, 40, 100 gigabyte VMDK around your data centers to replace your old production images. You know, if your application and dependencies are 20, 30 megabytes, then your Docker container is going to be 20, 30 megabytes. A lot easier to fire around multiple data centers to replace those images that have updates needed. And quickly, what containers are not. So we'll go into this a little bit later, but they're not microservices. Okay, we use the terms often together because when you're writing microservices, you need a way of very easily packaging up all those new services you're creating. So they complement each other well. But as I said, containers are just a packaging mechanism. If you want to put a 1980s monolithic Java application that's 200 megabytes big and it's a massive billion lines of code and it takes 20 minutes to start up and it requires 8 gigs of RAM, you could put that in a container if you wanted. It's just a way of packaging up your applications and dependencies. It's also worth mentioning, if you're not familiar with containers, if this is kind of the first you're hearing about containers and Docker, they are not, pardon me, they are not VMs. The modus operandi is very much the same, but they are just user space. They are just the binaries, the files, the libraries. You're still only running one server, even with multiple containers. You're not running VMs. So if your application does custom things with kernel modules and loading kernel drivers to support, you know, whatever your application does, containers might not be for you because those kernel modules will get loaded underneath the containers, and then they can't guarantee that those containers are giving you the isolation and the portability you want. But yeah, containers, building VM images, but with a much better developer user experience. So Docker build gives me a Docker image. Docker images shows me the images I've built. Docker push and Docker pull allows me to put that image basically somewhere online in a repository so that my production data centers can pull it down, either publicly so anyone can pull it down, or, you know, a private repository so it's just my internal data centers that can get that. And then instead of booting the VM, Docker run, give it an image we built in the build step, and that's it. And this can all happen on a developer's laptop. So, for example, here is the simplest Python application in the world. It is going to give us a horribly, 1996 plain piece of black text whenever anyone visits the application saying, "Hello, Cisco Live," in a web browser. It's just running a little web server. So this is my business critical application going on here. And then this is my Docker file from Python. Start with a container that already has all the dependencies and system libraries and things I need so that that container can run Python within it. The Python executable is there, it works, it has the dependent libraries. Add my application into the Docker image that we're building. So literally just find a file called myapp in the same directory as wherever I'm running this Docker file. Make it executable. run pip install, which those of you that code in Python know is a dependency manager. So the application depends on Flask. Pip install is going to install the Flask libraries into that Docker container. And then what do I want to happen when anyone in future gets hold of this image I'm baking and boots that, like booting a VM, runs that Docker image? Well, I want the container internally to run that command. And that's it. That is basically replacing that whole VM configuration management, yada, yada, yada I was talking about with, hey, take my files, this is how I want them to be put into the container, these are the dependencies I want installed in the container, everyone's happy. And then you do a Docker build, it goes and does all these things within a container environment, and what you end up with is a container image. So now I can say Docker run my weird container image, because they all just get UUIDs when you build them. And you can see that everything I'd expect if I ran Python on my local laptop and gave it that application, I can see the output from this container image, but all this is happening within that Docker container. If I gave you a copy of that image and you didn't have Python installed on your laptop, but you did have Docker installed, you could do Docker run that image and you would get exactly the same output, because everything that application needs is now contained in that baked image. And as you can see, with the horribly rendered screenshot, apologies about that, we can then go to localhost 5000, which is where the server's running, and we can see our Dockerized application. And so that is the basics of containers. They are a really good way of packaging your applications and making them portable, and meaning that it doesn't matter if the developer's laptop has different stuff on it than the production servers, because you're isolating just what you need for your applications. But Docker run is good for development, but it's not good for production. And here's why. I am obviously going to want to run more than one instance of my wonderfully important production application that you've just seen there. What if an instance crashes? I don't want there to be downtime. I want, like we do with pretty much anything. We want a load balancer. We want multiple instances of an application for performance and resilience and all that. I am not going to manage production by having, say, 3 VMs or physical servers and logging into the first one and doing Docker run my application, and then log off. And then the second one, Docker run my application, and the third one. So I end up with 3 Docker containers running the same code. And then I'm definitely not going to go, okay, what IP addresses and ports are those containers using on those 3 hosts, and write those down in a list and email the networking team and say, hey, can you give me a load balancer with these 3 IP addresses as the backends so that we can load balance across these 3 images. And then I'm definitely not going to pay one to sit there on those 3 servers via SSH all day and all night going, Docker PS, is my container still running or has it crashed? Nope, still running. Docker PS, is it still running? No, you're obviously not going to do that. As I said, what is it missing? Sure, we can create these images and we can, package them up really nicely, but it doesn't solve load balancing. It doesn't solve where do we put passwords and secrets and environment variables that we don't want baked into our code base. How does the networking work? Like, what if I need to run 2 containers and they both want to use port 80 on the same production? Like, how is that going to happen? As I said, what about monitoring and restarting these images? If my application crashes, I don't want to sit there manually restarting Docker containers. When I said I'd come onto microservices, and that problem of having, trying to use Docker to manually run these containers is exacerbated by microservices, because suddenly, instead of maybe 3 applications, maybe our front-end web server client-facing code, back in the old day with the 3-tier applications, and then a big chunk of application code, which is 1 application or 1 deployment, it'd be like 1 Docker image, and then a back-end database. Microservices basically guarantee that we are now going to end up with a whole host more applications, okay? Because microservices are about separating individual, hands up if you're familiar with what microservices are. Okay, a couple of you. Microservices is this paradigm where instead of writing 1 million lines of application code in 1 big app, we basically say, well, okay, what's this code doing? Let's take a ride-sharing service, Uber or Lyft, or pick your favorite, which is, or Facebook. There we go. That's a better example because it's on the screen. This 1 million lines of code, it contains code that does who's friends with who. It does code that does friend requests. It does code that does uploading a photo and adding it to my feed. Those pieces of code don't really need to know that much about each other. So why don't we separate those out into separate little applications that can talk to each other over APIs? And there's massive advantages to this. For example, who is going to be more useful day one to your company? If you hire a new developer, is it going to be the developer that has to learn 1 million lines of code before he can start reliably making changes that are going to work? Or is it a developer that has to learn 20,000 lines of code for one component? And microservices basically allow us to treat functions within our wider application as individual apps. As long as we don't change the API interface, the language that we give to the other teams that work on the other parts, we could come in one day and completely rewrite our component, let's say the photo upload service. We could throw away our Python code and we could rewrite it in Golang if we wanted to. And as long as that API that the other pieces of our wider application doesn't change, the other pieces don't care. We don't have to go and tell the other teams that we're doing this. We don't have to have them run regression tests on all their bits. As long as our API stays consistent, we can break our problem down, which means that individual development teams have to learn a lot less code to be productive. And also, individual components can be written in the languages and the strengths of that team, rather than the whole program having to choose a specific language, which is going to be hard for hiring, or you're going to have people maybe having to come up to skills on a coding language they don't know. So microservices are a really good way of breaking things apart. And I'm going to put a link at the end with the PDF and all the code samples I'm about to use for this. So by all means, read into all this text if you want afterwards. But it basically means, pardon me, it basically means that we are not just talking about Docker run 3 times. We are probably logging on to server 426 and running Docker run for the 1,000th time, because we probably have 100 microservices, and each microservice is its own Dockerized application, and we want to run at least a few of each of them for resilience, like I was just saying. So suddenly we have a problem where we'd be managing thousands of containers with the Docker run command line. And obviously that's ridiculous. What you're instead going to want is something that you can install across a pool of compute resource, be it bare metal, be it VMs, be it public cloud, private cloud, Raspberry Pis, whatever. And you are going to want that orchestrator, that thing you installed, to basically take command of that compute resource. So you can say once, hey, orchestrator, give me 10 running copies of this Docker image. If one dies, spin up another instance of that Docker image to replace it. Oh, and while you're at it, give me a software load balancer on one of my company's public IPs, and load balance across the currently active 10 Docker images when you get a request coming in. Oh, and also, allow the developers access to stream the logs from those container images without having to give them login access to the underlying servers. So an orchestrator basically does all the bits around Docker that we've just been describing as problems, which Docker natively doesn't do. You can think of Docker as kind of the packaging format and the build tooling, but realistically, if you're running them in production, you're going to want an orchestrator. And there are a few orchestrators. Obviously, Kubernetes is the name of this talk. We're definitely going to talk about that, don't worry. You might have heard of Docker Swarm, Docker Enterprise Edition, Apache Mesos Marathon, Mesosphere DCOS. These are all container orchestrators. They are a way of turning a pool of compute resource into a thing that you can say, hey, go and run my containers for me. Realistically, we're talking about Kubernetes because Kubernetes has one. Docker Enterprise Edition, which was its own code base for orchestrating things, now embeds Kubernetes as an option. Mesos Marathon with DCOS now allows you to run Kubernetes clusters on top of their platform. I think someone was saying Kubernetes is the second highest contributed to open source project after the Linux kernel. Just the community and the ecosystem that's grown around this orchestrator means there'd be no point learning anything else. If you're starting today, you're going to find more, skills for people you're hiring that understand Kubernetes. You're going to find more developers that are familiar with writing the scripts to push their applications to Kubernetes. Realistically, it's just going to help you on your container journey. And so what is Kubernetes? It's just a container orchestrator. It keeps our containers up, it scales them, it routes traffic for them, it does all that day 1, 2, 3 stuff that Docker as a tool set doesn't do. And how do you install it? It's just code. It's just like any other application you install. It's just that this one is orchestrating that Docker run and that networking piece. So, you can actually install Docker Desktop, which is a bit meta, I know. But when you install modern versions of Docker, the command line tools, in the settings, you can actually say to Docker, hey, run all the Kubernetes bits of code to give me that orchestration API, like in Docker containers on my machine. So I can play with the Docker, Kubernetes commands, I can play with having Kubernetes spin up my applications, and that's actually what we're going to be doing on the demo today. You're going to see Kubernetes running completely in my laptop. And you can get that by just installing Docker Desktop. Obviously, in production, that's useless. You want multiple hosts. You want your applications to be spread across those hosts, so if a host or a VM dies, your application stays up. But for testing, it's really easy. You can also, pretty much every cloud provider will now give you a managed Kubernetes. Hey, Google, give me a 4-node GKE Kubernetes cluster. Done. Same with Amazon, same with Azure, same with pick whichever your favorite cloud provider is. I don't want to offend anyone. Yeah, and equally, you can get that same kind of as-a-service API on-prem. So Cisco sells Cisco Container Platform, which is a curated hardware and software stack you can wheel into your data center, and it will give you the same kind of API for, hey, CCP, give me a 4-node Kubernetes cluster. Give me a second Kubernetes cluster for this different team over here. It's very, very easy to get Kubernetes wherever you are just because of its popularity now. Or you could install it yourself. You could roll your own. And if you're really interested in how all the bits of Kubernetes fit together, how it actually becomes an orchestrator, there's a great blog post series called Kubernetes the Hard Way, which tells you all about these bits of Kubernetes, the API server and the scheduler and how it manages state and blah, 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 blah. Unless your company makes money from look at my custom pretty Kubernetes cluster you're going to buy off me, I would recommend going the as-a-service route. The time it will take your developers to learn Kubernetes rather than just consuming the Kubernetes API is time you could be spending adding business value by containerizing your applications or writing new application code. Like, it's very cool, it's very techy and geeky and how it all works, but realistically it's a solved problem. Pretty much every provider, on-prem and off-prem, will now give you Kubernetes as a service instead of you spending 6 or 8 months messing up your custom installations and causing downtime anyway, which is the whole point of what we're trying to solve. So, finally, using Kubernetes. And it's only half of the talk because A, the context is important, I hope you agree, why we care in the first place, and B, it's actually fairly simple if you're not installing the cluster yourself, if you're just consuming Kubernetes as a resource from Amazon or CCP or somewhere on-prem. And Kubernetes is basically based around objects, whether you're using the Kubernetes CLI, whether you're using the APIs, all the CLI is basically a command line interface to the API, you're asking Kubernetes for objects, a desired state. So when you say, hey, Kubernetes, make sure I have 10 instances of this application running at any one time, Kubernetes is just going to try its best to achieve that desired state. If you ask for 1 million containers, and each container requires a gig of RAM, and you don't have 1 million gigs of RAM in your Kubernetes cluster, it will never achieve that state. It will try and schedule as many containers as it can and won't schedule the rest because you run out of resource. It'll obviously tell you that, and you can use the APIs to show that deployment hasn't achieved its goal, but it is just trying to achieve a certain state you tell it to achieve. And you do that with these components. And new versions of Kubernetes kind of add new objects. And the common ones are pods. A pod you can think of as Kubernetes literally just doing Docker run my container for you on a server somewhere. It is the simplest Kubernetes object. It's not going to run multiple instances. It's not going to create a load balancer for you. It's literally just going to schedule one Docker run somewhere in your Kubernetes cluster. So at this point, let's have a look at that. This is going to be fun. My screen has unmirrored. Here we go. Right. Everyone see that at the back? Is that large enough? No? Wonderful. How's that? Yeah? Cool. So, we already covered, this will look very familiar to you guys. We have this Docker file that we use to build our application. Our application, if we remember, was a very, very simple Python application. And we've already built that into a container. In fact, I can do it again, docker build dot. And we get a container image. And because I want to share this, I want Kubernetes to know how to pull this down. That's a horrible name, and that container is just currently on my laptop. So we're going to tag that image with a useful name. There we go. And we're going to push that, like I said, to a repository that holds container images. Docker Hub is the default one that the Docker command will use. This will now, TRXUK is my username on Docker Hub. It will go and push this version. I give it a version number, number 1. It will go and push this image to Docker Hub, okay? Dependent on bandwidth and Wi-Fi and all that. So what we will now end up with is this container image in Docker Hub. And it actually means that if any of you had Docker on your laptop right now, and you went docker run trxuk/helloclr:1, it would download that Docker image and run that locally on your laptop, and it would run exactly the same as it does for me. But we care about Kubernetes. So instead of doing docker run, what I can do is define a Kubernetes pod. And these are all just JSON or YAML documents. Kubernetes can take both via the API. And it's really, really simple. What we're basically saying is, hey, give me a pod. So that's a Kubernetes object for just doing that Docker run for us. Give it a name. You see why that's important later, like a label. You can make these up whatever you want. Add as many labels as you want to describe what this is. And then, hey, just give me I want a container, and I want to use this image. This image is basically the exact same image that I just built. It's just tagged with a different name and Docker pushed. So if I then take that and go kubectl create and give it that pod manifest, Kubernetes is going to take that and try and achieve that state. So kubectl get pod, my Kubernetes cluster. You can see I now have one application running. Okay, so let's have a look at the logs of that. Kubectl get log. Kubectl logs, and I'll give it my pod name. You can see it's doing exactly what the output would have done if we did a Kubernetes run. It's just our Python application running in that Kubernetes cluster. So I can also get a load more information about this container from Kubernetes. Kubernetes describe pod. I'll see information from the scheduler about whether it actually managed to schedule it onto a node or not, etc., etc., etc. I'll also see some things that are a bit weird. So that is not an IP address on my laptop. That is not an IP address even on the servers that Kubernetes is installed on, which happens to be my laptop. Kubernetes by default runs its own kind of virtual networking layer and just gives every pod an IP address on that virtual network. The plugins for Kubernetes on how you want to do that networking, whether you want it to connect hosts together via Lisp or normal layer 3 routing with like a routing daemon or BGP to your data center top of rack switches is all pluggable. There's an interface specification that allows you to do networking in Kubernetes for niche cases how you want to do it. But obviously I cannot get to that. If I try from my laptop and go to that, and our application container listens on 5,000, there's no route to my internal IP range for Kubernetes. So that's all well and good. Like other containers within the Kubernetes cluster would be able to reach that. So you can have microservices talking to each other on these private IP addresses. But what you're realistically going to want is one of the next objects. And one of the next objects is services. We basically need a way to provide external access to our pod because it's on these private ranges. So again, everything is just a description. So here we go. This is a Kubernetes service object. You see the selector is basically referencing that tag we gave on our pod earlier. As I said, you can call these whatever you want, but that's how the Kubernetes objects reference each other. So instead of having to remember what the individual pod name was, bearing in mind, we'll see that if we're telling Kubernetes to run 1,000 pods of a given application, and it's going to bring new ones up every time the old ones dies, it's actually going to start naming those pods dynamically. So the selector allows it to go, okay, this is a load balancer for any application running in our cluster that has the tag app my app. And it's very simple. It's just, hey, it's basically a definition for a level 4 load balancer. So give me a TCP port on 5000 and load balance across however many instances of my app I have. So again, kubectl create f service. Helps if you could spell, Matt. There we go. And kubectl get services. So we now see, we actually have two. The Kubernetes API itself is exposed from the Kubernetes cluster via a service. So you'll always have that one. And then we have my app service. And on a cluster that wasn't running on my laptop, this would be a pool of real IP addresses from either your cloud service provider or your, internal network's IPAM range. And the service would give a real IP address to each service if you wanted it to. Because I'm running my Kubernetes cluster locally, and I only have one IP on my local machine, it basically is mapping this instead to a port on my local machine. So if I go to localhost at that, oh no. Why is that not working? Let's debug. kubectl get pod. My app-new is running. kubectl edit service. My app-service. My app-new. Here we go. My selector's wrong. This load balancer is load balancing applications called my app. My application's tagged with my app-new. I'll save that service. That will dynamically update Kubernetes to make that mapping to the right app, and then we can get to our application. So you see, tags basically control everything. So that's an application running in Kubernetes. Now, the problem with it is, as I said, I only have one of them. That's pretty useless. What if it crashes? So the next object I want to talk to you about is deployments. Deployments are basically a higher level service. They basically wrap the pod object in more useful metadata. So with a deployment, it looks very similar. I still have this spec bit that you remember from the pod definition. I'm still giving it a container name, okay? And I'm still giving it everything else I was giving it. I'm still giving it an app label. The only difference is I can now say replicas. And basically the container object orchestrates pods for us, so we don't need to manually create pods. If I very quickly did create a pod, we've changed the code slightly. So check this out. If I created a pod that now not only, instead of saying hello, it gave the host name. Each Docker container, when you run it, just gets a dynamically generated host name within the container. We also have another path in our application, which allows us to basically kill the application. It causes the application to crash. So if I very quickly edit my pod manifest to run this other container, because I've created a container image of this new version of the code. It's called server 2. I won't be able to call my pod my app because there's already a pod called my app running. So if I now do kubectl create f pod, I now have my new application running, okay? And if I do a kubectl edit service, whatever that service was called, and I actually say, okay, well, now I want you to point to my new instance of the application, my app2. and I go and look at this application again. Was it my app 2? Am I going insane? Yeah, my bad. Demo gods are not on my side today, ladies and gentlemen. What have we got wrong there? Metadata name myapp-2, edit service, myapp-2. Looks pretty happy. Can describe the service, which gives us more information about the service itself, which will show us things like what endpoints it currently is redirecting to. So we should be able to see endpoints, none. So it doesn't think there's an application called myapp-2. I've probably messed up somewhere, but I'm going to move on in the interest of time. What I was going to show you is if I ran that shutdown, if I went to localhost that port /shutdown and killed that server, Kubernetes would not restart that pod for me. I'd do kubectl get pods, and that pod just wouldn't be there anymore. It's just like Docker run is a pod. If the container crashes, if the container dies, the Docker or Kubernetes in a pod will not restart that for you. The difference with the deployment, and again, we'll just refresh our minds by looking at that deployment manifest. We have an app deployment called myapp-2. We've given it a label myapp-2. It's using the same application, which may or may not work by the looks of it, but we'll give it a try. Kubectl create deployment. And now if I do kubectl get pods, you'll see these completely randomly named pods are appearing, which are managed by this deployment object. And I asked for 4 replicas, so I've got 4 replicas. If I do kubectl get deployments, you can see it's taking care of this desired count for me, okay? And because that was called myapp-2, let's create a new service. Myapp-2, can't remember what the old one was called anyway, so let's just call this myapp-2 new service. So now we have another service. Here we go, myapp-2 new service. It's on this port, like I said, that would usually be IP addresses, and it's 6 seconds old. So hopefully, with a bit of luck, we can now go to here, and we see this is load balancing to our deployment, okay? Because every single one of those pods that it's spinning up all have that same tag. So if I refresh this, you'll see my load balancer will, because they all have different host names, rotate through these, through these 4 instances, okay? If I do kubectl edit deployment, and I find the replicas and I actually say, well, I want this to be, I don't know, 15. You see that it immediately tries to make that state correct. And as those containers come up, we'll start seeing new host names in our list because the load balancer will dynamically just route to anything with that tag. So we can start abusing the shutdown path to this application now. And every time we hit it, it's generally just going to keep working because it's going to kill an application. That's going to get taken out of the load balancer because Kubernetes just will take them out if a pod dies. And it's going to constantly try and get back to 15 replicas. So if we go and do kubectl get pods, we'll see a few are completed and they'll disappear from the API view at some point, but new ones will be built either already created or very soon created to replace that. So we can pretty much hit this as often as we want in a real-world deployment, and your application's always going to stay up. Another thing you can do with deployments, you can actually tell it when an application is really ready. So for example, your application, your Docker container may start, but what if your application takes a few minutes to do some initialization? You can actually tell the Kubernetes deployment using liveness probes and health checks, which again, just go in that deployment manifest. Hey, this API, like ping like this URL within my application, like do a get, and only if you get this data back or a 200 OK from this endpoint, like a health endpoint, then add it to the load balancer. Because even though you've started the container, it might require a bit of time to initialize itself. And with that, you can also then expose health endpoints that do more dynamic things. So instead of just going, I'm ready, add me to the load balancer, you might have an endpoint of your application called like /health that actually reports a metric of how close to full like your code is in that Docker container for a given application. Like if you know that your application can only actually handle 100 concurrent users an instance, you might actually want to report that in /health that your instance of that pod is currently running like 99 users. And Kubernetes can then do autoscalers where it will go and manually change that replica number for you based on this data it's collecting from your application. So if you had 5 instances and all of them were above 90 users and you've told it that like 100 users is the maximum threshold, at like 80, it will start building a couple more pods. At 90, it will start adding a load more pods. At 100, and you can customize those rules so that your instances scale up and scale down with demand, which is really, really cool. So I want to quickly go back to the presentation and just cover a couple of other objects you will care about. Persistence is one of them. Applications generally, microservices, that pod might die. You don't really care whether it's one pod or a pod 80 or pod 90. Those pods are coming, going, and you can actually tell a deployment that you've done these health checks on to do a rolling update. So you can actually say, hey, I know we're running container version, Docker image version 1. I want you to start replacing those one by one with Docker image version 2. Take one out of the load balancer, kill it, replace it with a new one, check it's live, check it's ready, add that into the load balancer so that eventually we've done a zero downtime rolling upgrade of all of our pods for a given deployment. And that's because we expect container code to be talking to data services somewhere else. We don't expect you to be storing data in your containerized application. You have a database somewhere, and that's generally how the microservices model works. You don't store data because you don't know when those pods are going to die. That said, persistent storage is useful. For example, what's the point in having all this wonderful stuff if I'm still having to automate manually virtual machines to actually run my MySQL server and my Redis instances? So Kubernetes actually allows you to have block storage, and you can tell Kubernetes through a persistent volume claim, hey, whenever this instance of this container deployment comes up, always mount it to this NFS path, or this iSCSI LUN, or this piece of local storage. And so if a pod dies and it gets replaced with another one, that whatever it is, a pod of a Redis cluster, an SQL server, can actually carry on where it left off because it will have the same data disk that the previous pod that died gets. So persistent storage is really, really powerful because then you can actually start having your databases and your application code separate but running within your Kubernetes cluster. Another thing is ingress. We're at a networking conference where most of you will probably be networkers, right? Show of hands. Cool, awesome, welcome. Think of a service as a layer 4 load balancer. You give it a TCP or UDP port, and it will basically load balance those incoming TCP connections. Think of an ingress like a layer 7 reverse proxy. You use it in exactly the same way, but you have more control over what's hitting. You can make more decisions because you're seeing more of the data at layer 7. So ingress, instead of going, hey, I want a service, and a service has an IP address and load balances to this port, an ingress you can actually say, well, I have one ingress for 10 different applications. If you hit myapp.com/ login, that traffic will go to one container deployment. If you hit myapp.com/photo upload, an ingress service will allow you to actually make decisions based on the HTTP data. And that's kind of cool because you can start doing things like, well, I don't want to rolling upgrade my entire production yet, but I do want to maybe take 1% of traffic at random through that ingress and actually send that to my version 2 of my application, so I can start gently testing whether my application is performing well with a small subset of users. So there's some really cool routing and testing you can do with the control that ingress gives you. And realistically, they are like the bits you will need to get started with Kubernetes. The Kubernetes website actually has some fantastic learning materials. It gives you a web-based shell, kubectl, and you can do everything I've just done without actually having to install anything on your system, and it will talk you through, here's how you write a pod, a service, etc., etc. So I will leave you with that. I will also leave you with a few resting thoughts, some follow-ups. There's a couple of things you're going to want to do if you start using Kubernetes in production. And the first thing you're going to want to do is not be manually running kubectl commands. You're also going to get really annoyed having to do a Docker build, Docker tag, Docker push every time you change a single line of your code to build that new container image before you then put that container image on Docker Hub, edit your Kubernetes deployment manifest, and do kubectl create. What you're instead going to want to do is have a server sat somewhere integrated with your source control repository, so GitHub or whatever you're using, has CI/CD style automated build system. And what you're going to want that to do is, if your application code changes in your source control repository, have something else go, oh, there's a Docker file in here, I'll try Docker try Docker build. And then I will run whatever test suite's in your code base against a copy of that Docker file I've just built, the image, the Docker run. And then if that succeeds, I'll bother tagging it with a version and pushing that new image up to Docker Hub. And if that succeeds, I will then go and talk to the Kubernetes API to actually tell it, hey, do a rolling upgrade to this new version of this container. So CI/CD basically allows you to fully automate the process of, we have Kubernetes, we're using Docker, I change some code, I want to see that code live in production behind my service, my load balancer, without having to touch any of it. And if you want to play with that, the DevNet sandbox at developer.cisco.com has a fully pre-configured CI/CD sandbox environment that's free, that you can reserve, and you can go in there, and it includes a VM that's hosting a Git source control server. It's got a sample application that you can quickly edit. It's already tied into a drone CI/CD server that does that Docker build, does that Docker push, and actually a small Kubernetes cluster, which it then deploys into. So you can replicate that whole thing and play with that in our sandbox. All the notes are there. The code samples I used, I promised like ones that work, not the ones I was struggling with, are in a GitHub repository. A PDF copy of my slides are there as well. That just links to a shared public Google Doc. I have enabled comments. So if you want to ask me any questions or follow-ups, just post a comment on the side of that document, and I'll try my best to get back to all of them. And I've got a little bit of time for questions, but otherwise, thank you all so much for sticking around and listening.